Tapered optical fiber addresses challenge posted by Brillouin scattering. Tapered optical fiber addresses challenge posed by Brillouin scattering. You're listening to Technical News Reading, presented by Hakeem Alibokis Alexander on Spreaker, social podcasting, presented for World Reading Club in association with Uniquilibrium. This edition's reading focus comes to us from phys.org. It's titled, Tapered Optical Fiber Addresses Challenge Posed by Brillouin Scattering. It was published on February 17, 2023. Our first featured image shows the transition region taper waist of the optical fiber, both the inputs and outputs, and the caption reads, a tapered optical fiber created by University of Rochester researchers achieves strong optical acoustic interactions with long-lived acoustic waves. Credit Wendao Xu. When optical beams consisting of photons travel through fibers, they cause vibrations that generate acoustic waves, consisting of phonons. The phenomenon, called Brillouin scattering, has been harnessed by researchers to optomechanically couple acoustic waves with light waves. This coupling allows information carried by photons to be transduced or converted to the phonons, which travel nearly 1,000,000 times more slowly than light waves. Optoacoustic coupling has enabled researchers to read and manipulate the transduced information more easily. To date, however, many of the Brillouin scattering techniques researchers have used rely on standard fiber geometries that cause acoustic waves to die out quickly, limiting the efficacy of the coupling. Now, using an optical fiber with a micron-sized waist, University of Rochester researchers have demonstrated how to couple propagating optical waves and long-lived acoustic waves with strong optical acoustic interactions. This is a unique and desirable combination that has not previously been achieved, says Wendao Xu, a PhD candidate in the research group of William Renninger, assistant professor at Rochester's Institute of Optics. Xu is the lead author of a paper in Optica describing the breakthrough. The breakthrough enables information carried by a light pulse to be temporarily stored in slowly propagating acoustic waves long enough for a second pulse of light to read the information. The achievement could have applications for light storage, radio frequency photonics filtering, and optical delay lines. The research achieved Best Presentation Award at the Wombat 2022 workshop on optomechanics and Brillouin scattering at the Max Planck Institute for the Science of Light, where it was presented by co-author Arjun Iyer, also a PhD candidate, in Renninger's lab, and that would actually be Arjun Iyer. It's an I. Arjun Iyer, also a PhD candidate in Renninger's lab. Wendao, Arjun, and our collaborators at the University of Tokyo did a great job in demonstrating the promise of this new platform, and we are all excited as we begin focusing on next-generation devices and real-world applications, Renninger says. Brillouin scattering in optical fibers, overcoming challenges. The amplitude of the acoustic wave keeps decreasing as it travels, Xu explains. Basically, all the high-impact Brillouin scattering that people are dealing with right now produce strong interactions, but the acoustic waves are high in frequency, in the gigahertz range. The higher the frequency, the shorter the wave can actually travel before it dies out. Shu's tapered optical fiber device achieves both strong interactions and longer acoustic lifetimes. It consists of a multi-mode glass fiber with the cladding coating removed. By heating the center of the fiber and simultaneously applying mechanical tension to stretch the fiber at both ends, Shu and his collaborators produced a tightly confined symmetrical waist in the fiber. This waist provides an ideal optomechanical overlap yielding the strongest Brillouin coupling strengths observed to date from a fiber taper and comparable to the largest optomechanical coupling strength for any system, the paper notes. Moreover, the lifetime of the phonons that the device generates, about 2 microseconds, is long enough that information carried by a light pulse can be temporarily stored in this slowly propagating acoustic wave for a relatively long period of time before a second pulse of light reads the information. A tapered optical fiber device. According to Ayer, Shu's achievement is twofold. One is the system, the tapered fiber device, which supports an acoustic wave family that people didn't pay a lot of attention to previously, he says. The other is the process itself, using an interaction between two different optical spatial modes to get what we wanted. The process, including the physics involved in achieving strong interactions with long phonon lifetimes, could be adapted and applied immediately to improve existing technologies, he says. For example, detecting and filtering out unwanted radio and frequencies in photonic filters, or producing fiber optic transmission delays to compensate for delay differences in optical fiber systems. The tapered fiber system, on the other hand, while useful for research, is likely too fragile for real-world applications outside the lab, Ayer says. These are micron-sized filaments of glass that are just hanging there, he says. However, the researchers are already exploring ways to package the system for real-world applications, Ayer says. For more information, look at a paper from Wendao Shu and others titled Strong Optomechanical Interactions with Long-Lived Fundamental Acoustic Waves, published in Optica 2022. This was provided by the University of Rochester. You've been listening to Technical News Reading, presented by Hakeem Alibokis Alexander on Spreaker, social podcasting, presented for World Reading Club in association with Uniquilibrium. This edition's reading focus has come to us from phys.org. You can read this article and others like it for yourself by visiting phys.org. That's phys.org. phys.org. Tapered optical fiber addresses challenge posed by Brillouin scattering.